The last thing that I would like to show is the calculation of frequency responses for three-phase systems. So, as before, I would like to start from the list of variables, in particular the small signal inputs and the small signal outputs. So I have selected the three-phase alternating voltage as inputs and also potentially the direct voltage as input. Likewise, for the outputs, I have considered the three-phase alternating current and the direct current, which are so actually the common modes. Common modes, direct voltage, common modes, direct current. I can work with a single input, single output, for instance, from phase A voltage to phase A current. If I run this, so of course I'm not looking for shift transfer functions, just the no shift one. It tells me that it has unrecognized field LTI. This is because if you want to calculate frequency responses, you first need to go through the whole procedure of linearizing and frequency lifting. So we have done a collocation calculation. We have done also some sequences calculations. This is just for the display of the waveforms. Actually, this is not required to do the frequency response calculations. Let's just make the symbolic calculations and linearization. Then calculation of the periodic matrices. For bigger systems, you see that calculating the Fourier coefficients of each matrix takes a little bit longer. Then frequency lifting, likewise, generally I can work with a ht equals to hm, so 6, but I keep it smaller for the purpose of presenting the toolbox. Calculation of the harmonic state space model. The system does not have internal delays. And I see that I have indeed 4 inputs, 4 outputs times their number of Fourier coefficients, total of 34 non-lifted states, meaning 238 states lifted. And then I can finally calculate a frequency response from the harmonic state space model. I run this part, and this time, of course, it works and gives me the frequency response in which I am interested. I see that having no delays, there is no high frequency non-passive region. And then likewise, if you want to see the admittance from direct voltage to direct current, well, this would be example DC side, change the sign factor, and I directly get the frequency response. Still no non-passive regions at high frequency because we don't have delays. But since we are working with three-phase systems, at least from the perspective of the AC side, there is something else that I have implemented, is the multi-input, multi-output three-phase frequency response calculation. So I will say example, yeah, I can keep this name. Again, I don't have to specify underscore A, underscore B, underscore C. If I give it VG as input variable name, it will look for VGA, VGB, VGC. Likewise, for the outputs, I do not have to specify ISA, ISB, ISC. It will automatically look for it. So these are calculations that are specifically dedicated to three-phase systems written in terms of ABC variables. So at least that the ABC variables of the inputs be in the list of inputs, and that the ABC variables of the outputs be in the list of small signal outputs. And I am just going to run this part of the code with Control-Enter, and here are results. So what I'm displaying here are the positive, negative, and zero sequences relationships. So positive to positive, negative to negative, 0 to 0, and all the other off-diagonal components of the positive, negative, 0 sequence transfer function. Because these are very small, they are actually equivalent to 0. So I would only, if I had to study this, I would only focus on those that have a significant magnitude. So the positive to positive and negative to negative, and I could ignore all these other relationships. Naturally, for different systems, it is possible that you'd have other interesting information in these relationships. But in any case, so this is only one of the plots that you can have in the DSA structure, in particular under frequency response. We have more information. So from before, we have the example on the AC side, the example on the DC side, but this time we also have our multi-input, multi-output, three-phase example. If I look into this identifier, I have, as before, name of input variable, name of output variable, the sign factor, input channel, harmonic shift, frequency values. If I looked into the harmonic transfer function, this is what I have. It's a 28 by 28 over 1000 frequency points. Why 28 by 28? Well, because if we look at the harmonic state space, this is exactly what we had. 4 outputs times 7 for coefficients gives 28 outputs, and same thing for the inputs. So this is technically the complete input to output harmonic transfer function with all the couplings that you could have in the linear time periodic system. In the harmonic linearization, this is where the whole transfer function is split into its no shift part. Harmonic linearization, we have one multi-input, multi-output, and one single input, a single output structure. Let's have a look first at the multi-input, multi-output. Here we have the for this particular variable to that particular variable, the ABC to ABC no shift frequency response, which is this a three-phase frequency response, a 3x3 matrix for every frequency point. We also have the one from 0 positive negative to 0 positive negative, which is again a 3x3 matrix for every frequency point. You can also extract directly all of these, all of the underlying single input, single output frequency responses by looking at the CISO single input, single output case. And here they are. You can directly, use these data to plot them. I'm making just one example figure. I would plot, let's say, the magnitude of this particular transfer function, which I will find here. A to A. It will just be a magnitude. I'm not putting it in a logarithm. And against this, I would like to see the frequency. So this is something that I can find here. Naturally, if you put this in a logarithm scale, as well as the magnitudes in dBs, then you can have the plot that you want. This is just one way of showing what it can look like. You can definitely make your own plots. And one last thing is that although I have not automated Nyquist stability assessments, nor the generalized Nyquist stability assessment, this is something you can do with all the data that are produced by the toolbox. In that particular case, you will have to consider one given system, make 2 instances. So let's consider a very practical example from my thesis. Let's see if I want to apply Nyquist on this particular system. then I would have to make a split point at some location, let's say here. Then I would have one system, but I would have one instance, let's say for the HVDC link, and one instance for the offshore grid. I would solve for the periodic trajectory of the complete system. Then I would split between the, then I would get the frequency response of the HVDC link as seen from the offshore wind farm. And then I would have a frequency response of the offshore wind farm as seen from the HVDC link. That would give me two sets of frequency responses, potentially multi-input, multi-output, and then I could use the generalized Nyquist criterion to analyze the overall stability of the system. This is in case you are interested in doing some frequency domain stability assessments based on Nyquist, but naturally do not forget that the toolbox is initially intended for state space time domain representation. Hence, the main advantage of working with this toolbox would be to go to an eigenvalue calculation, regardless of whether the system has delays or not.